Hello and welcome to AI4. Our next session is going to be led by Dr. Raul Rodriguez. He is the Dean of School of Business, Professor of AI, ML, and Robotics at Woxsen University. Please join me in welcoming him to the virtual stage. Welcome, it's all yours.
Thank you so much for the introduction. Let's kickstart the session, which is surely going to be interesting. We will keep it, of course, to the basics without going too much in depth. We will run through the key areas of, or the key aspects to be discussed within the 3D printing of bionics and, of course, of organoids in this case. As you can see in the title, we are going to work across deep learning, which is, of course, the in-depth area of machine learning utilizing neural networks, particularly CNN. And we'll see how this evolves across the stages and what kind of research has been done and what personal research I have done. So the first aspect which I would like to discuss with you in brief is what are we going to discuss about today? The index. First, we're going to speak about why are organ transplants an urgent need, why they are required, and why do you need to be concerned about this. There are several areas of research within deep learning that do not affect or involve the biological aspects of human beings. Rather, they focus more on certain aspects such as autonomous vehicles, music recognition, and so on and so forth. But why should you focus and why should you be concerned about healthcare and why deep learning is such a critical factor in this particular industry? We'll see that. Then at the same time, we analyze how exactly has this research been evolving in the last years, what has been done so far, not particularly in the 3D printing of organoids for enabling the learning, but more on the basis of 3D printing of organs and how the area is evolving across the years, and obviously how is this helping in the further development of this critical area for us for ensuring survival as well as ensuring longevity of human beings. And lastly, an area which is my particular field of research, which is quantum computing, or in this case, quantum AI. So how exactly quantum AI algorithms, in this case, deep learning induced algorithms, will impact the biological factors and will impact the 3D printing of these bioorganoids, and well, how will it evolve? Because there is a transition, as you will understand, from the 3D printing, which is the basics, to deep learning, which is the middle ground, we can say, and then landing into the quantum computing arena, which is the most advanced arena, which we still have not reached to at the moment due to, well, lack of infrastructure and lack of resources, but it's hopeful that we will do so in the near future. So let's kickstart. First of all, as we discussed earlier, why are organ transplants an urgent need? I mean, we all know that organ transplants and donations are critical to the survival of n number of individuals. But what we need to understand is why is this area of research in particular very important? Not just because you will end up saving lives and you will not just end up fasting up the process of obtaining an organ, but also you will ensure that the organ will match the host, that there won't be any sort of rejection, and that the particular organ composition and cell distribution will match the particular host perfectly without any chance or any percentage of inaccuracy for rejection. So to start with, I always like to start with a quote. So you can see one of the quotes by Dale Carnegie in terms of the most important things in the world have always been accomplished by people who've kept on trying, and of course without any hope. And you will see why I have kept this quote is because in this particular area of research, hope is minimal, since at the end of the day, doing primary research and collecting primary data on this arena is pretty complicated, since you need to actually test it on human beings rather than just lab. So lab testing can be successful, but in the field, it can be pretty challenging. So you need to bear this in mind, and hence the hope can be questioned. And at the same time, the accuracy of the results can also be at the same pair a challenge. So you need to keep this in mind. But if no one starts this area of research and no one really involves quantum computing into it, obviously nothing will take place. So there is always a step forward to be taken. Now, if you look at the US particularly, Of course, this affects every country, but if you look at the US in particular, there's an n number of patients in the waiting list, waiting for various organs, especially kidney, lung, and pancreas. There are others, such as less common, we can say, which is eye donation as well, and eye transplant. So these particular organs, there are a number of them, as I said, but the main ones, as we all know, are the heart, lung, and pancreas. Can really save a lot of lives, and you can see it in the screen. Over 100,000 lives can be saved if we really fasten up the process and making accurate. And it's not just the fact of the waiting list, it's also the fact that even when the organ transplant happens, there can be possible rejections in the short as well as the long term. So in order to avoid this, utilizing deep learning, and especially quantum deep learning enabled algorithms in order to predict various compositions of the organ is so critical. So with this introduction, I just wanted to make you aware of the criticality of these aspects and why this area of research is so fundamental for the future of healthcare, beyond the basics of AI and beyond the basics of deep learning. Now, if you look a bit more at technical aspects, the actual algorithmic composition as well as the healthcare-based composition, there are going to be two steps in which deep learning will help. So let's look at the screen and let's look at how exactly these steps are distributed and interconnected. So the first step, as you can observe, will be the generation of a blueprint. What do we mean by a blueprint? We mean by the structuring of features, of patterns from the original X-rays, in this case, whichever X-rays and cell distribution and composition of the original organ that we may need to create, because we are at the end of the day creating it from scratch. And then generating a blueprint. What is a blueprint? Similarly, when you have architecture and you have a building, or you are in the infrastructure and construction sector, you have a blueprint of the building, a distribution, a floor plan. Similarly, we need a floor plan as well here for the organ generation. By floor plan, we mean size, the particular composition, the blood group, the particular types of cells, RNN, DNA, and so on and so forth. There are several components to be impacted in this area. But the blueprint is really extremely critical area, which depends in a huge measure on the spectral data, which we obtain from the feature extraction. This is the first step. Second step, which will happen simultaneously, will be the guided 3D-PP. Now, what is a 3D-PP? 3D-PP is a short form for 3D body printing. So here we get on a more hardware-oriented area, which is the 3D printing area, which I will discuss shortly. So in this particular arena, there are going to be two key steps, sub-distributed into three. The first one will be optimizing the parameters. So we have certain parameters established, as well as in the first step, but we have certain parameters established. We transfer this into a predictive modeling graph, and in order to observe where the distribution takes place. And then the landing area will be the 3D body printing, and all of this will can combine in order to ensure that there is an accelerated advancement of tissue fabrication. As you can see it on your screen, that is the key aim here. So first, blueprinting, generating an accurate, determining an algorithmic-based blueprint. Then at the same time, you optimize the parameters, you optimize the data, you optimize the creation of the organ, and both of them combine. The end goal, which is anyways the end goal of the whole research, is to accelerate and to create a sort of unprecedented advancements of tissue fabrication. Because what is complicated is not to create the organ. What is complicated is to ensure that the organ matches the host, to ensure that the speed at which the organ is being created is accurate and is up to the mark and is up to the standards required. We cannot take a long period of time, and in fact, the aim is to create it at the shortest period of time possible, for obvious reasons, in order to, of course, ensure that the waiting list is lesser, as well as the risk of losing that particular individual is eliminated. So as you can see, there is a lot at stake here, a lot of risk, and a lot of difficulties we can incur, obviously, at the same time, because we are dealing with biology. What is being used in terms of techniques, in terms of parameters, in algorithmic features or algebraic features? Well, first of all, we are going to use something called rapid prototyping techniques, or in short, it could be short as RPT. Now here in the rapid prototyping techniques, we are going to focus on the printing, on the actual physical material. Now, why is this area so critical? because nowadays 3D printed organs are using various materials. Some of them are fitting the human body in terms of hosting it. Some of them are not. Some of them are accurate to the host. Some of them have been rejected. Now, some of the materials which have been proven to be accurate and well up to the standards are collagen and gelatin. Now, these two particular materials seem to be fitting the regular human structure and the regular human distribution without any rejection. So this is an important area, the physical area. If we move into the computer science-based area, we have the neural network, which we will mainly rely on. There are others. There are plenty of neural networks which you can rely on, especially GNN, generative alternative neural networks, as well as the CNN. So focusing on the CNN, which is the short form for convolutional neural networks, here we will focus upon the image identification and pattern identification. What do we mean by this? You take the X-rays, as we saw before doing the parameter optimization, we select what patterns are accurate and fitting and differentiating that particular organ from that person in correlation with the general organ distribution. We transfer this data into the system, into various algorithms, among which I would like to highlight two, which is in your screen, and then we identify how the particular 3D printed organ has to be structured, distributed, what composition, so on and so forth. Now, what algorithm are we going to use and why? First of all, let me tell you that the evolutionary as well as the genetic algorithm that you can see on your screen are both belonging on the same branch. They both come from the same family of algorithms. Why am I putting them differently? Because each of them will have a different use, though they have a common origin. Firstly, the evolutionary algorithm will be used mainly for planning models. What do I mean by planning models? Simulation. If you talk about simulation in this case, we can always do what we can call in more of a colloquial language, a trial and error on the computer as well as on a 3D printing machine. Obviously on a lab setting, not on a realistic setting. So in this case, we will use it for planning the models, estimate accuracy of the organ, and of course, estimate the accuracy that the organ is not going to be rejected by the particular individual's body. On the other hand, if you look at the genetic algorithm, here the focus will be the DNA and the RNA sequence of a particular organ. So we will focus a lot here on the assembling part when it comes to the mutation and adaptability to the host. So as you can see, they are both interrelated, but each of them has a particular and very independent function from each other. One will focus on simulation, the other one will focus on DNA as well as RNA composition and assembling. Mutation, I'll tell you why, because once there is an adaptability to the host, there has to be a mutation as well of a particular cells in order to adapt to the biological distribution and composition of the body. Now, all this might sound very fascinating in terms of computer science as well as mathematically speaking, but how do you do this in real life? What particular cells do you utilize? You might have heard the term pluripotent stem cells, or in short, stem cells. Now, a stem cell is what gives birth to most organs as well as bones and most of the body composition of human beings. How and why do we use stem cells? Firstly, we use stem cells because obviously we need to recreate new organs, and to do so, we use the key area, the mother cell, which can create these organs, firstly. Secondly, how do we use them? Well, to compose and to create these particular 3D organs, we are utilizing the materials mentioned above, along with stem cells, which will be injected in the printed organs once produced, in order to reproduce within the same organ, as well as recreate the same composition in the host's body. So the whole aim here is to, one, recognize the patterns. Secondly, simulate that the organ will actually fit the host in the particular case scenario, based on age, and based on physical disturbances, physical issues that the person might have, so on and so forth. There are a number of areas to be covered here, of parameters to be analyzed. Then we will jump into the DNA and RNA area. And lastly, which is at the end the key, because without the stem cells you cannot really perform, it will be the utilization and involvement of stem cells in the whole adaptability as well as mutation process, which is obviously the end game here. Now, in the screen you can see a sample. This is a sample done by an Israeli company. Now, where I'm going to show you this sample, this is a 3D printed heart. Obviously, this heart is of the size of a rat's heart, approximately. It's not a human-oriented size, nor is meant for human use. But why I'm showing it to you is because a 3D printed heart, produced with a regular 3D printer, will look something like this if you print it at a particular scale. The aim is to obtain something like this, but with a human size oriented area. At the same time, get it in a very short period of time. As per research and estimations I've been able to complete in the lab setting, the estimated time for a 3D printed organ utilizing deep learning or quantum AI in this case will be an average of 40 to 45 minutes. If of course, in the lab setting, and if the conditions are adequate. Obviously, this has to be tested in real life, so there is a lot of scope left to be done. But in the screen, you can observe how a 3D printed organ will look like, with all the arteries and veins involved, and with a fully fledged functioning within it. So as you can see, it's fascinating what we can really achieve in this arena. Now, what has been done so far, not particularly on the area of heart printing or liver or pancreas in this regard, but more on the vision-oriented printing. There are various universities as well as various private institutions focused on this research who have focused mostly on the retinal transplantation. Now, why is this important? As you know, many people, especially in countries like India or China, where the population is extremely vast, there are various cases, in fact, several cases of retinal distribution and retinal problems derived from diabetes as well as other vascular issues. Now, this is critical not just to avoid individuals from becoming blind, but also to avoid any sort of secondary problems such as, well, brain tumors, even eye tumor can land into the same. So to avoid this particular the deficiencies in the eye, there is a very, very critical area of research from which I got not inspiration, but from which I got the adequate research inclination towards 3D printing, which is regenerative therapies. Now, this is called regenerative because you're planning to regenerate the eye composition or even transplant eyes or generate new eyes in relation to the eyes that the individual has. And in order to, of course, introduce and transplant a healthy eye for that matter. This is called in vitro because it's done in the lab, but it can also not be in vitro depending on the context. In this case, with the eyes, it has to be. And by the accuracy compelled by various researchers across the years, the accuracy with CNN, again, convolutional neural networks, is from 0.87, which is pretty significant and optimistic, especially in the area of vision or eye-oriented printing, because as you can imagine, it's a very critical as well as delicate area of the body, and the accuracy has to be extremely huge. And you can observe in your screen there are various areas of the eye which will be critically determined and very, very affected by any sort of research or printing that might go wrong. So accuracy is of extreme criticality here. Now, how can exactly quantum algorithms help in this regard when it comes to healthcare and when it comes to the future of the healthcare industry involving quantum algorithms and quantum deep learning? As you know, quantum AI is a combination of quantum computing as well as artificial intelligence. But in this case, we're going to just talk about the area of quantum computing and then see how it relates to the area of deep learning, which is what we have been discussing till now. What do we do by involving quantum here? Basically, we will involve main 4 aspects. There are many more, but to highlight 4. One will be the stream processing of large amounts of data. In fact, it will be 20 times faster than the actual or regular deep learning algorithm. Secondly, the actual correlation and modeling that we spoke about earlier with evolutionary algorithms will be extremely more developed, both in terms of accuracy as well as speed. Then on another aspect will be the mutation as well as adaptability and regeneration. So in case there is an issue with the organ, the regeneration will be automatic. So that is the aim, is to create organs that will regenerate themselves in case of any sort of issue, or once transplanted, of course. So that's why stem cells are very critical. And if we can train this particular algorithm to develop deep learning induced stem cells using the wonderful speed of quantum. Obviously, the regeneration as well as mutation can be achieved in a tremendous manner and in a very short period of time. And lastly, we have the analytical power. We are going to utilize neural networks, which is the best of deep learning at the moment. And then we are going to use the best of quantum, which is the maximum speed that you can achieve. To conclude my presentation today, I just wanted to give you a heads up on what countries could be actually tremendously impacted by this research and by these results. Most of you might think about your own country, of course, be it the US or others. But if you look at the number of population and the amount of citizens in each country, as well as the amount of organ transplants that occur in these countries and the length of a waiting list, the main countries which will be actually impacted will be, for starters, the US, then Brazil, then India, and China. Now, this is not by any sort of coincidence. This is simply because of a correlation, a simple statistical correlation of population versus organ transplants, as well as the waiting list length. So, considering this, you can imagine what kind of a population in the world will be really impacted by this, and how many lives we can really save, or not just save, but improve in the short term. The aim is to create any sort of impact in the next 5 years, to test it in the real life setting, not lab setting, in the next 7 to 8 years, and obviously have it in a full-fledged implementation in the next 10 to 15 years without any delays in this regard, and with the full impact of quantum AI. So this will be everything from my end. So now, of course, any questions you may have, please feel free to ask.
Thank you so much. A big virtual round of applause for you. Thank you. We learned a lot in your session and we appreciate you participating. All right, if you're looking for your next session, feel free to check out the program page, and you can also take some time to do some networking while you're online. Thanks again, and we'll see you around.